The last two sections were about exponential growth and exponential decay. Today we're going to talk about a very specific kind of exponential growth or decay, but it's going to also go back to the compounding lesson that we did before in Chapter 7. It's going to kind of combine these two, and we're going to look at a very special kind today. For 9.3, continuous compounding is what it's called. So the question for today is there a limit to how much you can earn in a bank account in a year, no matter how many times it is compounded? So remember, compounded is how many times they calculate your interest to give you within a certain year, within a year. Sometimes it could be 4 times a year if it's quarterly. We did monthly was 12, every day was 365. So is there a limit to how much you can get as we increase the number of times it's compounded in a year? That's the big question. And that's going to give us something very special for this lesson. So let's recall the general compound interest formula. That would be A equals P, which is principal, times 1 plus R over N to the NT. And hopefully you remember what all that stuff means. And if you did not remember this formula, it is also just right down here in this table. So here's the question. Suppose we're going to make it really simple by just using basically ones everywhere. Suppose we had $1 to invest in an account, and the bank's going to give us 100% interest rate, which is like the most we can make, right? 100%. Complete the table to see how much money you're going to make as we increase the number of times it is compounded in 1 year. So we have 1 year, $1, 100%. So we're going to see ones everywhere. The only thing we're going to change is the number of times it's compounded. And so here's our list over here. We have the compounding frequency. So annually is 1 time per year. I filled that in for you. So that means with the principal is $1. The rate is 100%. So 100% moved over twice is just the number 1. So here's 1. If it's being compounded once per year, the 1 is in the N as well, which is on the bottom and the top, technically here. And then 1 up here is also the T. So it should be 1 times 1 or just 1. Putting that into the calculator, that means you would get $2 after your first year if it was 100%. Right? So they'd look at your dollar, they would say, okay, we're going to match that, give you another $1, so you have $2 now. So what happens if we increase the number of times it does the compounding? So if we did semi-annually, that means twice a year. So again, $1, 100% is still here. We're only changing the N value, which occurs up here and down here. This is also being multiplied by 1 year. I just didn't show it. So it's still 2 at in the exponent. Calculate that, you get $2.25. Now really this 1 out here, it can almost be ignored because 1 times anything you get in here is going to be that number. But I'm going to set it up like that every time, and then we'll do the calculation. Quarterly means our N value is now 4. So nothing really changes besides the N value. So it'll be 1, and then times 1 plus 1 over 4 to the 4th times 1. So 4 times 1. There we go. And then I'm just going to put it in the calculator and see what you get. So 1 plus 1 over 4, and raise that to the 4th power. So if they did it 4 times in 1 year, we would go from $2.25 to $2.44. Okay, so the first time we did it, we went up from 1 to 2, we got 25 cents. Now we didn't even get 25 cents, so it's a little less. So you can see like we're still growing, but it's just not as much. All right, so what if we jump up to monthly? That would be 12 because it's 12 months in a year. So I'll set it up the same way I did before. It's 1 over 12 to the 12 times 1. It's times there. So I'm going to change this to divided by 12 to the 12 times 1. So this one I got 2, whoops, what is going on here? 2.61. Yeah. So again, we jumped up in some money here, but not even 20 cents this time. It's kind of getting less and less. So it seems like as we get less and less when we increase this number, we're going to eventually kind of get to a very specific number. So we'll see. Daily, so now we're really going to jump up. We went from 1 to 2 to 4 to 12. Now we're going to jump up to 365. So I'm going to change these two numbers to 365. So 1 times 1 plus 1 over 365 to the 365 times 1. Okay, I'm going to put in my calculator. And now I want to go ahead and I think I want to write out some more decimal places because you're going to see that this is going to kind of give us the same number here. So we have 2.71. I'm going to go a little further so you can see how it changes as we get a little higher here. Then it goes 4, 5, 6, 7, 4, 8, 2. I know it's money, but I wanted to show you how this long decimal and how you'll see some things will kind of stay the same. If we go to hourly, so we're really increasing the number of times we compound per year, we'd have to figure out what that is, first of all, right? 365 days, and there's 24 hours in every single day. So I'm going to do 365 times 24. That's going to be 8,760. So that would be 8,760. That's how many hours are in a year. So 1 times 1 plus 1 over 8,760. 8,760. 60 times 1. All right, let's see what we get here. 1 plus 1 over 8,760. So I'm typing it in myself. 8,760. All right, so this is why I want to put all these decimals out, because we get this again. 2.71, 8, 1, 2, 6, 6, 9, 1, 6. So I don't know if you noticed, but it's the same number as far as your money is concerned because it goes out to 2 decimal places. The only place it starts to change here is after the 1. 2.71, 2.71, and now these numbers are different. Okay, so we're going to go one more time and go by the minute. So if hourly is 8,760, that's how many hours there are in a day. We're going to multiply that, since there's 20 or 60 minutes in 1 hour. We'll multiply that by 60. So now we're going to go up really high, and the minutes would be 525,600. That's multiplying this number, the number of hours, by 60. So here's a setup. And this is the last one we're going to do because this gets pretty big. 525,600 to the 525,600. Squeeze it in there. And I'm going to type it in the calculator and we'll see what we get. Okay, so I got 2.71 82792427. So is there a limit, if we keep going up and we keep raising this number and changing these two numbers in here, is there kind of a limit as to how much we can make? Well, certainly. What's happening every single time we increase the number of compoundings per year is we're kind of setting more decimals in place. So right now we have 2.718. That showed up down here again. If we were to go even higher, this number would start. The next decimal that we would have gotten probably would have included a 2 and maybe even a 7. So as you get more and more and more and more, it's going to keep kind of setting these numbers in place. And as you keep increasing it, it ends up being just one specific number. So the number it gets close to has a very special name to it, and we give it a special letter. This value grows closer to a specific value we call E. Use the letter E. The E value is approximately 2.71828, and it goes on forever. So it is very much like pi, 3.14159. It goes on forever. This is a very set number, and anytime you see E, that's the number. So it's just like pi. It's an irrational number. Irrational means it goes on forever, doesn't repeat, and is used for interest that is compounded continuously. The title of this lesson, compounded continuously. So anytime it says compounded continuously, we actually have a new formula we're going to use. which will be down here. So why do they use the letter E? Well, it is named after this person, which you would think is Euler, but it's actually pronounced Euler for some reason. Some person a long, long time ago, hundreds of years ago, in like the BC era. He proved that this sequence of numbers here, or if you just change the n value like we've been doing, as you get bigger and bigger, this number approaches 2.718 as you keep increasing the n. So as n increases, it keeps getting closer and closer to this number here. So he proved that. So where does that come into play with our money? So now we have a new formula. It's called continuously compounded interest formula. A lot of the stuff is the same, but it actually, to me, is less complicated than the other one. If you have an amount P invested in an account, paying an annual interest rate R, so these letters are the same, the amount you have in the account A after T years is this. A equals your principal times E raised to the power of RT. But don't forget, E is just a number. You could just as easily put here the number 2.71, that's one right up here. Up here. 2.71828 ... right? That's all it is. It's just saying it's just this number raised to the R times T. So anytime it now says compounded continuously, we're going to use this formula as opposed to the one back here. We're still going to use this one. It just depends on whether it says continuously or one of these other ones here. So we'll try one, and we'll do a team huddle. Example 2. Katie invested $3,927.54 in a bond paying 5.5% compounded semi-annually. After 30 years, the value of the bond will be $20,000. How much would Katie's investment have been worth after 30 years if the interest were compounding continuously instead of twice per year? So this is giving us a lot of information, and some of it we don't really need for our formula. So they told us our investment, so that's our P value. They told us the interest rate, that's R. We got to move it over, though, twice. And they also said that she did it semi-annually, which means twice a year. That's where this comes into play down here. So after 30 years, T, she had $20,000. We're going to compare that amount to the amount she would have gotten if it was continuously compounded. So we're going to compare that to continuously compounded. So I'm going to use our new formula. A equals, the way I kind of remember this is it looks like the word PERT. It's P times E to the RT. PERT. That's a new one. Okay. So we're going to have A equals. Now, I honestly don't know. Oh, yeah. On my calculator on my phone, I do have E to the X on there. And if you're using the calculator like from school, it has that on there as well. So if you see the E button, you can use that. You might have to turn the phone to the side to see more things, but I have it on mine. So this is starting out at 3,927.54 times E, keep it as E. The exponent would be 0.055, and the time is 30 years. So let's see what happens. You can put that all in at once. 3,927.54 times E to the 0.055 times 30. So I got 20,450.62. So we answered the question. How much would Katie's investment have been worth after 30 years if she did it continuously instead of twice per year? She would have actually made an additional $450 because originally it was only $20,000, but now she's up to $20,450. So if it were compounded continuously, she would have made a couple $100 extra within 30 years. So it's not really that much, but every penny helps, right? So you have a huddle to do. The first huddle, you're going to use A, B, and C like you normally would. So you're still going to use this formula. I already messed it up, I think. P times 1 plus R over N to the NT. That's used for all three of these. This is the one with the new formula because it says continuously. That's where you use PERT. So just to be aware, we're using both formulas in this particular case. 2 is very similar to the one that we just did. You're comparing if they use it twice per year to compounded continuously. All right, moving on to example 3. So we're going to see what this graph looks like. So consider the function f of x equals e to the x, which is similar to the above interest formula. First off, is this an exponential growth or decay? Well, how do we determine that? We look at the b value and see, is it greater than 1 or is it between 0 and 1? Well, what is the b value? It's right there, e. So this is a lot like saying f of x equals 2.71 ... to the x. So is it bigger than 1? Yes, it is. So this will be a growth function. We're going to use a graph calculator and graph it, and I'm going to answer the following questions. So I'm going to go ahead and use Desmos, throw it in there, and it does recognize the letter E. If you type this in, y equals E, actually it gives you the number right down there, to the x. So here's your exponential growth. It also goes through 0, 1, and I'm just going to make a sketch of this. I'm going to actually bring up a table maybe. There we go. Pretty ugly. Whoa, there we go. These numbers are all pretty ugly except for 0, 1. So I'm just going to maybe make a sketch of this because the points are pretty bad. Okay, so 0, 1 is a point, and then I'm just going to make a sketch. Going up like this. Okay, that was terrible. It's a little better. So this is your standard exponential growth graph. This looks the same as the ones we did in 9.1. So let's answer the following questions and see what we got. Since it's growth, it's no different than a normal growth formula, a growth equation. So just because it has an e in it doesn't make any difference really. So domain, it goes forever to the left, forever to the right. Again, we can look at Desmos, right? It's the same idea. This one really does shoot up though. It's going to go forever to the right, even though it kind of goes slowly, and it goes forever to the left. And remember, if you zoom in, this should be getting closer and closer to the x-axis, but it doesn't actually touch it. Domain's the same thing. All real numbers, so nothing changes here. Range, it doesn't touch 0, so it's 0 to infinity. The y-intercept, that also has not changed. The number out front here, if you don't see it, is 1, so it goes through 0, 1. I'll just say 0, 1. Growth factor, that is your base value here, which would be e. Or you could say the 2.71 ... X-intercept, there is none. Like all other exponential functions, there's no x-intercept. And the asymptote would be at the x-axis, where it does not touch. All this stuff is very familiar, very similar to before. Okay, so how do you actually tell if e to the x is growth or decay? The one we just did was growth. However, you can get decay out of e to the x. So here's what you're going to look at. And this is only for e to the x. If the exponent is positive, so in this case, we just had positive x, then we know the graph is growth. If the exponent is negative, then the graph is decay. And I'll show you why it's decay in our examples down here. So this is the first time we're actually going to look at the exponent to see growth or decay, because the base value of 2.71 does not change. We have to look at the exponent now. But this is the only time you do it. Example 4, state whether each equation is growth or decay. All right, so I'm going to give you this example here to show you what's going on. Now, normally when we have a negative exponent, we would know how to kind of start this by hand. I could rewrite this as putting it over 1 and flipping this. So you'd have 1 over e to the 2x. It'd be positive now. So what do we have? We actually have 1 over the number 2.71 squared, basically, with an x on it. So what that means is 2.71 squared is just going to be a number. So you get 1 divided by that number. So this number in here is less than 1. So this is like your b value, but it's less than 1. If you were to divide it by 2.71, whatever it is, squared, you would get some kind of small decimal. So every single time you get a negative exponent, what's going to happen is it's going to flip this and turn it into a fraction, and inevitably that will be a number less than 1 every time. Okay, so this is going to be a decay. So that's kind of the reasoning behind it, and you don't have to do this every time. You just have to memorize this little box here. If it's a negative exponent, it's decay. B, this is a positive exponent because it's 4.5. So this would be like literally saying 2.7 raised to the 4.5 power. And you could actually solve that and get a number, but it's going to be a positive. So it's going to be growth. And it's going to be greater than 1. And the last one, same idea. You could rewrite it as 1 over e to the 3x. And now we have a decimal less than 1 decay. So remember that for only exponential with e. All right, to Huddle, and I think we're done, right? Yeah. I'm going to kind of go over this real quick. I know I want to kind of be done here, but I want to go over one of these problems in the Huddle. This one, you're actually going to graph e to the negative x, which we know is decay. And you should be able to see that if you can put it in a calculator, or you can use Desmos. So I want to kind of go over these ones because they might mess you up a little bit. State whether the following functions are growth or decay, and then state the y-intercept and growth factor for each one. Okay, so we didn't graph any of these, but you should still know, like, this is the a value, this is your b value. Same idea. You're supposed to state growth or decay. Okay, so this one is a positive exponent, so it's growth. Y-intercept would be the front number, 5. Growth factor is, so now we have to include the exponent, anything but x. So if there's a number in the exponent, we have to include that in our growth factor, so it's e squared. Okay. Very similar for part B. I think you can do that one. One that I want to talk about is the last one down here. So look at this. Exponent, well, I just circled the whole thing, but the exponent, 3x, that's positive, so it's a growth function. Growth exponential. And then the y-intercept is the one out front. That's your a value, 2/3. And then your growth factor is actually e to the 3rd power. So you have to include the exponent as your growth factor. We haven't used any, we haven't done any problems with something in the exponent besides just x. So make sure you include that in your growth factor. And that's the only time you have to do it, because all the other ones you're going to see, when it doesn't use e, it just has x up there. I'll do, how about one more? E, so now we're just looking at just the number. This is like from earlier sections. 4 divided by 5, that would be 0.8, I think, right? So that's definitely less than 1, so this is decay. Y-intercept is the first number, 24. Growth factor is 4/5. So you can finish off the rest of those to turn in the lesson for 9.3. And now we'll finish it for continuous compounding.